respected Professor A. Ramchandra garu, and my dear colleague Praveen, and my dear students. Good morning to all of you. I extend a warm welcome to everyone present here for today's extension lecture. The Department of Chemistry has planned a series of seminars, webinars, and some extension lectures during this academic year. And as part of this initiative, today we are organizing an extension lecture on interaction of radiation with matter, the origins of spectroscopy. I sincerely thank Professor A. Ramchandra garu for accepting our invitation to deliver this lecture. Ramchandra garu is a distinguished professor of chemistry, highest academic grade, retired from National Institute of Technology, Warangal, with a remarkable academic journey spanning over 37 years of teaching and 42 years of research. He is known for his contribution to electrochemistry, coordination chemistry, molecular spectroscopy, computational chemistry, and chemical science education. He completed his PhD from University of Hyderabad and joined NIT Warangal as a faculty member in 1985. An accomplished researcher, he has guided 15 PhD scholars, authored over 50 research papers, presented more than 65 conference papers, and supervised 128 master theses. He has completed 15 sponsored research projects worth 1,255 lakhs rupees, has authored several laboratory manuals, books, and instructional materials for the chemical science students. Ramchandra garu held numerous key administrative positions, including Dean, Head of the Department, members of the Board of Governance, Coordinator of DST, Coordinator for Teaching Learning Center, Chairman or member of academic communities. He is also widely known as a passionate science communicator, have delivered over 500 popular science lectures, contributed extensively to newspapers, and served as editor for Vigyan Vani Science Monthly. And he is also awarded several awards from the central government, state government, and some NGOs for his contribution for the chemical sciences. Even after retirement, Sir has continued to contribute science communication and academic outreach, remaining active with organizations such as Jana Vijnana Vedika in Telangana Academy of Sciences also. With great pleasure and respect, I now invite Professor A. Ramchandra garu to deliver his lecture. Thank you.
Thank you, Dr. Koteswara garu. Good morning to all of you once again. I think that you must have come from several parts of the country. Is working? No, does not seem to be. How many of you actually have come from non-Telugu states? Please raise your hands. Those who have come from other states other than Telugu. Apart from whatever Dr. Koteswara has mentioned, I am also proud to say that I am one of the founders of Jana Vijnana Vedika and also the founder editor of one of the important Telugu Children's Science Monthly and Chekumuki. Perhaps some of you must have written the Chekumuki talent test when you were in the schools. And some of you must also read some simple answers in Inadu daily. For nearly 25 years, I was answering questions to children's questions. Actually, they used to ask some questions in I Bujji. There was a column called as I Bujji in the Inadu and the Induku Yemiti Yala. So I used to answer those questions along with Professor E.V. Subbarao, who is no more now, of course. So this is about other things because I am more equally passionate about science popularization and developing scientific temper among the people, especially the secular views, also unity and diversity concepts, and anti-obscurantistic attitudes. They are also important in the society. That's why We are also proud to be associated with the Jana Vijnana Vedika, which is a national award winning organization. Being the president of that organization in 2005, that organization has also got the highest national award. I was the president of that. And we went to Rashtrapati Bhavan, and from the hands of Abdul Kalam, we received the award for that organization. Now, I'm equally interested in making some of the difficult concepts in science in a lucid way. That's why I requested Dr. Puteswara Garu. See, most of the important thing for chemistry is molecular spectroscopy. Those who are actually mastering one or many of molecular spectroscopy techniques, they are going to find some kind of gainful employment anywhere. There are actually hundreds of spectroscopy techniques, both atomic level spectroscopies as well as molecular spectroscopies. Maybe atomic spectroscopies maybe very, very simple, maybe a handful few. But molecular spectroscopies are going to be exposed, maybe not less than 50 or 60 different kinds of spectroscopy techniques are available in the current science and technological world. And you know that chemistry is taking place in chemistry were able to make life very simple. That's why you must be very proud to have taken chemistry as one of your branches or maybe one of your subjects. And in case you are going to be specialized in chemistry in your PG courses and all, you must be much more proud. Because chemistry is going to provide some kind of livelihood or not. Definitely it will provide some livelihood. So be proud to be a chemist. And since chemistry is called as natural science, and the chemical investigations, chemical analysis, material diagnostics, and going into the depth of how the matter is composed of, these things are going to be important because one of the natural laws is that why different materials behave differently, why they appear differently, why they taste differently, why they are present in different states of matter, gaseous state, liquid state, maybe solid state, etc. Why? What actually makes them to occupy or to select different kinds of physical states in a given temperature and temperature and pressure. All these things are going to be decided by the chemical environment, or chemical composition, chemical maneuver of the atoms inside. So you know that whatever materials we see around are either elements or compounds. Okay. So how do you know what kind of elements are actually present in a particular molecule? Or the molecule, what kind of arrangement is there for the atoms to be linked by? For example, you know, in organic chemistry, we talk about isomerism. See, with the same composition of elements, different kinds of compounds are likely to come. For example, acetone and propanol are actually isomers. So propanol is an alcohol, acetone is a ketone, but the number of carbons available in acetone, number of carbons available in propanol are same. Number of hydrogens, number of oxygens are also one oxygen anyway in both of them. But there are different compounds. See, similarly, like in English, suppose you have got a 4-letter word, 4 letters, MEAT, let us say. How many ways in which you will be able to make a that's a combination and permutation of these 4 letters? I can say MEAT, you can call it as meat, which we non-vegetarians eat. You can also make it as a team. You can also make it as a mate. You can also make a team. So like that, several things are there. So same 4 atoms, MATE, these 4 atoms, depending upon the way in which they are combining, which is first, which is second, which is third, which is fourth, and all different meaningful words are coming. Same way, different atoms are going to be joining together to give different types of compounds. Then how do you know that? Because you cannot see the atoms, you cannot see the molecules. Molecules and atoms are so small, such a small thing that your panchendriyas will not be able to identify where they are. So you need to have a tool. You need to have some kind of device. You need to have some kind of paraphernalia by way of which you will be able to go deeper into that, even though you are not able to see the molecules and all. So somebody will be mediating between you means between our 5 sensor organs and the fellow which is not being visible to us. That is nothing but the spectroscope. And the mediator is mostly, there may be electrochemical mediator, there may be other sound mediator. For example, there is one thing called as a photoacoustic spectroscopy, where sound is going to be the mediator. And mostly the mediator is going to be light. So to understand the light or the light-based investigation of materials, mostly it is spectroscopy. There may be a lot of other things. For example, microscopy is there. That is spectroscopy. We'll be able to send the radiation through some lensing materials, some kind of optics and all. So because of some refraction and all, we are able to magnify the small things from a micro level to something like macro level. You are able to get that. There's a physical phenomenon. There's nothing like that spectroscopy. But the light-enabled perception of unseeable or undetectable, unperceivable material is mostly through spectroscopic techniques. That's why I have chosen a technique called as interaction of radiation with the matter, and that is how is going to be a starting point for the development of various kinds of molecular spectroscopies and also the atomic spectroscopies. But before that, where is my PPT? So please just put the PPT. See, before you go for that, you must understand one thing: the concept of field. Okay, not the agricultural field and all, where there may be several kinds of fields depending upon the type of crop you are growing, cultivating. Different kinds of land fields may be there. But in the scientific world, the field means something that influences other thing. Okay, for example, I am able to stand very firmly here. I'm not falling down. I'm able to withstand the gravitational pull. I'm not going to the center of the earth. But that is something called as a gravitational field is there. And see, for example, light is there. So this is all called as the electromagnetic field. So okay now. So there are actually 4 kinds of fields. I told you what's going to be field. Field is some kind of spatial zone, a spatial domain, a spatial existence where some effect will be there on some kind of particle or some kind of object or a material. Depending upon the nature of the material, depending upon the type of field you are talking about, some interaction will be there. So if there is a field, it will be having some effect on its own genetic material. Genetic means not the biological genetic I am talking about, the same kind of chemistry. Again, chemistry means not the type of chemistry what I mean. So the intimacy, the relationship, or the so-called a son and daughter, maybe a father and a daughter like that. So some kind of family member. So the field and its family member will be influencing each other. That's what the meaning of field is. So now I'm going to tell you. Okay. For example, if there is no field law, the object is going to be remaining there only. Actually, this kind of things, no. See, this is another interaction. This is an LED scale. Now, on an LED scale, a laser beam will not be reflected. See, will not be. Whereas it's coming from here. So that's called as scattering. So the scattering cannot be done on an LED. LED is a bubble, a small bubble is there. Okay, light emitting diode. So light emitting diode will be actually there are several light emitting diodes. The laser light will go in between. So there is no reflecting zone. If I am putting 2 fingers here, there is no finger here. No, there is no material at all. So if it falls over here, it will not be reflected. It falls here. It itself is light. So it will not be reflected. That's why I am not able to put laser light over there. So there is no way of marking. Worried about that. That is one of the other things how light is to be perceived of. So this is the field. You can see in this field now, there is no field. When there is no field, any object that has been kept here will be staying put. No movement at all. Suppose there is a field like that. And this is field friendly. The field friendly, I will just talk about that later on. This is field friendly. If it is field friendly, what will happen? There is going to be some kind of influence on that. Previously it was here, but because there is a field, it has got some kind of influence. So that is the meaning of field. Okay, there are 2 kinds of fields. One is a static field. For example, all of us are existing in the gravitational field. We are able to stay here, and if I am just putting it, it's going to fall down. But this is called as a uniform field. Okay. If I am putting 2 different kinds of objects, heavy and light one, both of them are going to be reaching the ground simultaneously. It's because of the uniformity felt by this particular object, uniformity felt by this particular object, and they are going to fall down. They are not going to be falling down in an inclined way. They are not going to be going whatever you are having is a static field. See that way. Whereas there are some fields where their influences are going to be changing. So it will be pulling up, it will be pushing down, it will be pulling up or pushing down. So like that, like a pendulum, the field also may be behaving. So that's called as a oscillating field or non-uniform field or heterogeneous field or anisotropic field. So light is actually an anisotropic field. The radiation, whatever you are getting here now, it is an anisotropic field and it's called as electromagnetic field. But before that also, let me tell you some more things. There are actually in the entire universe, whether it is an atomic world or your house or here in this hall or entire India, or maybe in the entire Asian continent or anywhere in the Earth or in the solar system or in the Milky Way galaxy or anywhere in the universe, from micro level to macro level. Do you have the color mic so that I can make some kind of movements? I don't have to stay here like uniform field. I would like to make some kind of physical movement here and there. Generally, sir, do you have a color mic?
No.
Okay. Okay, so there are actually four, what's water house? Four fields are there. And any phenomena, any occurrence, any happening, any instance, whatever it may be, flowers blossoming, crop maybe rising up, and we embryologically growing up. So some iron object getting rusted, light coming, thunders, bolts, meteors, lightning, whatever it will. Whatever you see, whatever you call it as a happening, all this happening in the universe are possible only because of four kinds of forces, or four kinds of fields. They are all strong nuclear force field, weak nuclear force field, gravitational force field, and also electromagnetic force field. A force is, from Newton's first law itself, you know the meaning of force. Force is something that influences the body. Okay, it may be different kinds of fields. The forces can be, need not be only gravitational force. Forces can be electrical force, magnetic force, and nuclear force also. But there are these two forces called as strong nuclear force and weak nuclear force. They are going to be operative only within the atomic nucleus. The size of atomic nucleus, you know, it is only 10 to the power minus 15th of a meter. What is meant by 10 to the power minus 15th of a meter? You know, 1,000th of a meter. 1,000 meter is called a millimeter. Maybe the maybe some kind of nail that is coming out that you will be cutting with the nail cutter. No, so that much is going to be millimeter. And that millimeter, if again you are dividing 1 lakh crores of times, 1 lakh crores of times, again you divide 1 millimeter, then you are going to get a so-called femtometer at 10 to the power minus 50th of a meter. That is going to be the size of atomic nucleus. And these two forces, called as strong nuclear forces and weak nuclear forces, are going to be making their judgment, making their drama, making their influence only within the small domain. They will not be coming out, they will not be opening up their behavior, their face outside the atomic nucleus. So you have to forget about that. So whatever you see around, you are able to see me, I am able to see you, you are able to see the plants being green, you are able to see the rose flowers looking rosy, and we are able to see somebody dying, somebody is becoming born, and we see a lot of other things. No, all these are within the purview of gravitational field and electromagnetic field. So everything, and I can challenge you as a volunteer of Janavijaya that you tell me one incident happening anywhere in the universe. Sir, that particular phenomena is nothing to do with gravitational field, nothing to do with the electromagnetic field. It's something to do other than these two fields and all. Nobody can come out with their claim. That's the way you have to appreciate. Okay. Then I told you the meaning of a strong nuclear field. They are operating only within the nucleus. Nuclear field, they are operating only within the nucleus. And gravitational forces field, they are operating not only in the atom, but also outside the atom. And similarly, electromagnetic fields are also there. They are operative not only in the nucleus or atom, but also outside the world. And within that electromagnetic field, again, there is a exclusively electric field and exclusively magnetic field. But electrical field and magnetic field are always like the two sides of the same coin. Hereafter, we are going to be minding our business in this particular external lecture only on this electromagnetic field, because light itself is that. So interaction of radiation with matter means radiation, the synonym of radiation will be light. So whenever I use light, you have to think it as a electromagnetic field also. Whenever I say electromagnetic field, it should also immediately in your mind think that it is light. Sir is talking about light. So light and the electromagnetic field or electromagnetic radiation are all synonymous. Okay. That is the way you have to appreciate. And this is the way in which you make some kind of comparison among those four fields. As I told you, strong nuclear force. So if you take this as a unit, and with respect to that, let's call normalization, like in the JE ranking and the NEET ranking and all, people normalize. So whoever has got highest mark, no, that will be set as 100. And with respect to him or with respect to her, how other students have performed. And 99, 99.9, 99.8. So that way, with reference to that particular highest fellow must not have answered all the questions. Out of 100 questions, he must have solved only 78. And 78 is the highest mark, let us say, in the country. Then 78 is set as 100. With respect to that, other 76 fellow, 55 fellow, 35 fellow, how they are actually related to the 78 mark fellow. That is the way, kind of normalization. So, with respect to strong nuclear force, I am normalizing. If that's the case, where does the electromagnetic field vary? So the next more powerful field or force, that is something that is actually making some influence on an object, is the electromagnetic field after strong nuclear. Okay, then where do you come across this strong nuclear field? The domain is only within the nucleus, ranging to 10 to the power minus 15th of a meter. As I told you, it's a platform or the so-called dais, where strong nuclear force will be making some dance and singing and performance and all. Is going to be a small, narrow dais, a narrow platform. And what is that due to? What kind of influence does it do? It actually makes the protons and neutrons stay together within the nucleus. It also actually it offers actual mass. All of us are having mass. This also has its own mass, maybe half a kilogram. I am now 80 grams kgs. So Earth is something like 6. After 6, you have to put 24 zeros. That kilograms is the Earth mass. So who is actually offering mass to this matter? What will come across? That is because of the strong nuclear forces, the so-called gluons, gravitons, quarks, bosons. The standard model is there. So strong nuclear force actually is responsible for the mass and placing the protons and neutrons together. Even the protons are having identical charge, and such in a narrow space, they are able to stay together, stay put without getting repulsion. According to Coulomb's law, you know that the light charges repel, but in spite of being very close, the protons are not repelling. Okay, hydrogen is a single proton, nobody is there to repel. But other elements have got multiple protons, but still they stay together. So what is the force for that? That is the strong nuclear force. Then electromagnetic force may be 100 times more influential than the strong nuclear forces. But that is all this electricity, magnetism, atomic bonding, chemistry, entire chemistry is going to be mostly due to this electromagnetic forces. Then weak nuclear forces, okay, they are going to operate. Their strength is 1 millionth of the strong nuclear force, and that is responsible for the radioactive decay. So you know the meaning of radioactive decay. So the radioactive decay are maybe the neutrinos, which are supposed to have no mass at all sometime back. And recently, 5-6 years back, Nobel Prize also was given to have discovered that neutrinos also have got some mass. Okay, and that is due to the weak nuclear forces and gravitational forces. And they are going to be very, very weak. See, after 0.001 you have to put 37 zeros and 1. That much weak ness is the gravitation. But that weakness, even though on this board it looks very weak, the Earth is revolving around Sun by that only. The Earth, the entire solar system is actually making a motion within this Milky Way galaxy by that. Several galaxies are able to interact with each other because of that. I am able to grow up against the gravitational field because of that. So gravitation is everywhere, but it is very small in quantity. Okay. And the way the fields have to be appreciated. Electrical field and the magnetic field are actually called as polar fields because they have got a direction and also opposite also is there, bipolar. Positive charge is there, negative charge is there. Positive electrical is there, negative electrical is there. Okay. Magnetic also, north pole is there, south pole is there. So there is always dipole, magnetic dipole, electric dipole is there. So that way you can say that the electrical field and magnetic field are polar, means the poles are there, dipole, means excess, less, up, down, like that. And they have got attraction repulsion. Identical charges repel, unlike charges attract, this kind of things are there. Whereas the gravitational field does not have any dipole. There is no positive gravitational field, negative gravitational field, and there is no gravitational dipole and all. So that way, gravitational field and nuclear fields are all non-polar fields. So again, I told you that we are going to bother about the electromagnetic field. In case you are having a field like that, maybe a positive charge over here, like a battery. Suppose you take two plates and connect the two plates by a battery, maybe your dry cell, and you are actually creating an electric field into that. Into that electric field lines are also there. In case you are sending any charged body like that, it may be influenced. It may be, it's not going straight. So according to Newton's first law, any object moving with uniform velocity will be unattended to in case there is no force at all. But it's not going unattended, it's going bent. So it means there is influence. So that is because of the electrical field. Similarly, there may be some magnetic field also. There is a magnetic field also. And a charged body also is going to be influenced by a magnetic field. So a moving charged body is going to be influenced by magnetic field. So that is the way in which you have to appreciate the concepts of the fields. And in the beginning, I told you the meaning of static field and also dynamic field or oscillating field. There may be some fields which are oscillating in a sinusoidal manner. Go up means increasing and again decreasing, again increasing and decreasing. So if I put a body like that, maybe a charged body, because a charged body will be influenced by electrical field, but the electrical field is such a type of one where it is oscillating, which means to say that there is an oscillating electric field around. That's the meaning. Because this is our point reference, maybe our what is a model or our perceiver or representative. By looking at its motion, we are able to understand what is the unseeable field inside. Okay. Similarly, there may be a magnetic field, and the magnetic pole is going to be influenced like that. So you can think of anisotropic magnetic field isolatedly. You can think of anisotropic electrical field isolatedly. But the light, whatever we call as the radiation, which is going to interact with the matter, is simultaneously oscillating electrical field and also magnetic field. So you will not be able to separate them together. An oscillating electrical field will be generating an oscillating magnetic field. An oscillating magnetic field will be generating electrical oscillating field. So they are going to be mother and daughter. So we don't know which is daughter, which is mother. Both are having same age. But we can, by varying gravitation, by varying magnetic field, I can create electrical field, varying electrical field. By having electrical field, a varying electric field as a starter, I can create a varying magnetic field, and vice versa. But electrical field oscillation and magnetic field oscillation are going to be coexisting together like the same sides of two from sides of a coin. So you will not be able to separate them. So that way, electrical field and magnetic field are going to be together. They are not independent. And there is how do they change? Okay, electrical field. What is light? How do you distinguish light? I told you light is simultaneously oscillating electric field and magnetic field. Okay, then what do you mean by that? How does it change? It changes by this equation called as Maxwell's equation, okay, where this is called as intensity. How much effectively it is powering up and how much effectively it is powering down. So that is called as the wave intensity given by psi. Sometimes the psi must have come across in the quantum mechanics also, where psi is called as the electrons finding zone or electron waves probability zone. Okay, psi square is the probability zone. Electron wave intensity is called as psi. But the psi is psi. Okay, the psi letter can be used for identifying the intensity of any wave, whether it's matter wave or radiation wave, sound wave, or wave. So the rate of change of double rate means second derivative of the amplitude with respect to time is going to be equal to the wave propagation, how effective the wave is propagating from the source to outside, maybe away from the source, and in time and also in space. That way, the light wave is a simultaneous propagator of space and time. I will tell you what's meant by propagator of time and space. Okay. There is a light here in front of, above me, there is a light. Suppose that light is here, somewhere around the pyramid, okay, maybe around this particular depth. And in case I am having a charged body, one coulomb, or maybe one electrostatic unit, one charge is there, maybe electron or proton, or any charge, maybe sodium atom, or maybe hydrogen atom, like proton. Now, if at all really there is a light is coming this manner, I am still here only. I am not making a movement, but I put my clock on, stop clock on. So this is my charged body. I am staying here only. If at all there is light, if at all the light is made up of a simultaneous electrical and magnetic field coexisting, the meaning is this. Since this is a charged body, and since this is an oscillating electric field, here at this moment, it goes in this manner, at this position. So time is going on, time is going on, time is going on. It started with 0, now 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. But this 1 second, 2 seconds, 4 seconds, 5 seconds, 8 seconds and all, I am mentioning only. But suppose you are drawing a graph, 0, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, etc. It's going to appear like this. 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 5 seconds. So at 1 second it was up, second is down, third second is up, fourth second is 0. So that way, a sinusoidal wave propagation with respect to time can be thought of. So on x-axis I can have time that way. So I am positioning fixed, my position is fixed, but time is varied, and with respect to time it is changing. Now you just freeze the time. You freeze the time. The light is there, and it is going on with respect to time. You don't know. Now you freeze it. Once what is meant by freezing? Time is not a moment. Now at a fixed time, maybe at the fourth second, let us say fourth second, at fourth second I'm fixing it. Now what happens? You put the charged body somewhere closer to the source. So this is going to be influenced by the field. No, it is going to be going up, going down, going up, going down as I go away from the source. So as I go away from the source means position. At this position it was 0. After some it has gone up. After sometimes again it is 0. After sometimes gone below. Again it come forward to the 0. Up and down with respect to space. So 1 meter, 2 meters, 3 meters, 4 meters, 5 meters, 6 meters at a given time. So this is that. So I can say 0 line, 1 centimeter, 2 centimeter, 4 centimeter, 5 centimeter. So that is going to be the type of curve with respect to the field intensity I'm going to get. So the top red line is a sinusoidal variation of wave intensity with respect to space and time. Similarly, I can think of magnetic field also. If light is there, if this is a unit magnetic field means unit magnetic pole, north pole. So if I am staying together here at a fixed position, with respect to time, makes a movement. Maybe the magnetic field is going this way, going up, going down, away, through, away, to and fro, to and fro, to and fro, like that. So then this may be the type of thing. So 0 time, 1 second, 2 seconds, 4 seconds, 5 seconds, 7 seconds, 8 seconds. So x-axis is now on time. Similarly, the same magnet is going to be making here 0 towards you with respect to space. Again 0 going away from you. Again 0 going towards you. Again 0 going towards away from you. Again null. That way, with respect to space also, a magnetic pole is going to be making its rhythm in case there is an oscillating magnetic field. So both in terms of time as well as in terms of space, there is sinusoidal variation. That is the meaning of oscillating magnetic field. As I told you, light is simultaneously both. So what does it mean? So this is the way. So this is the magnetic field, and this is going to be electrical field. So together they are going to be coming like that. There is no independence of that. Whenever there is an electrical field, there is also magnetic field. Like that. And the distance between identical position at one point and another identical position immediately next on the path, on the spatial path is called as wavelength. So radiation has got some concept called as wavelength. Okay. So like that. So this is at a given point in space and time is the sinusoidal wave, and also at a particular time also the sinusoidal wave. So this is again same equation. So that is the magnetic field and the electric field. So peak to peak distance or trough to trough distance, and magnetic field lines of peak to peak are null to null. So null to this is also null, but this is a rising null. Immediately after this null, there is a rising point. But immediately after this null is a falling point. That's not the identical point. So from here to here also wavelength. From here to here also is wavelength. From here to here also wavelength. From here to here also wavelength. Okay, fourth and fifth line. From here to here also wavelength. Wavelength means the distance between identical consecutive phasial points. PHASIAL. Phasial means phase. What is the rhythm of the wave character? And from you have just started at one phase means wave's behavior, and look for the next identical phase immediately. The distance between that in space is called a wavelength. So concept of wavelength, simply don't think that crest to crest, trough to trough is wavelength. That's okay, that's one way. But that is not alone the wavelength. Wavelength could be the space or the distance between identical consecutive phases. That's how you have to understand the meaning of phase. Wavelength. Okay, then the radiation also has got some property called as velocity. Okay, in vacuum, where there is nothing, there is no air, no glass, no water, no benzene, no permanent solution, etc. Then this is start wavelength, mid wavelength, high wavelength. So I am only giving some visible radiation. It could be any kind of maybe ultraviolet also, maybe X-ray also. So the waves, irrespective of their wavelengths, are going to making same kind of speed in vacuum. So the speed of light is independent of wavelength in vacuum, but that is not the case in some media, like materials, like glass, like water, and all. Even colored solution also. So they are going to be having different kinds of velocities. Generally, shorter wavelengths will be moving sluggishly. Longer wavelength things will be moving briskly. That's why we are able to get the light dispersing from white light. Since white light is made up of several colors, since the speeds of the various colors are not same, so they will be coming out at different times out. So naturally they get dispersed into identical different colors. That's why jar is coming, that's why your rainbow is coming. So that is the reason how to understand. So the characteristics are like frequency. Frequency is from a given point in time. 1 second time, how many waves are actually going out from the test position? That is the meaning of frequency. Number of waves ejecting out from or select point is called as frequency. The meaning of frequency has to be understood that. And the wave number, how many waves are there in a unit distance? If you're setting CJ system as a units of distance, maybe in 1 centimeter, how many waves are there? You can see 1 wave, 2 wave, 3 waves are there. So 3 waves are there in this particular diagram. It may be 4 waves, it may be 10 waves, it may be 25 waves. But that wave number is nothing but the number of waves projecting, number of waves present in 1 unit distance. Generally, in MK system, we take a meter as a unit, but mostly in spectroscopy, molecular spectroscopy, you take centimeter as a unit. So, in 1 centimeter, how many waves are there? That's called wave number. So, frequency has been understood, wavelength has been understood. Okay? Wavelength has been understood in this manner, and the frequency has been understood in this manner. Then the wave number also has been understood in this manner. So, depending upon the wavelength or the frequency or the wave number, different zones are there. So, remember, wave number and frequency are proportional. H is C nu bar is energy. Okay. E is equal to H is C nu bar, where C is the radiation velocity, nu bar is the frequency. Hc by lambda is also energy. Since C by lambda is nu, H nu also is energy. So you can say that the light energy, optical energy, electromagnetic energy, if you call it as E, can be proportional to the frequency, where H is called as the universal constant, called as Planck's constant. So frequency, if it is proportional to energy, since the frequency and wavelength are inversely proportional, C by lambda. Okay. So naturally, since 1 by lambda is a nu bar, so nu bar and energy are proportional, nu and energy are proportional, lambda and energy are inversely proportional. That is the concept, mathematical, simple mathematical knowledge you should also have. So depending upon the frequencies or conversely the wavelength or conversely wave number, different zones have been created. And now with respect to wavelength, I am now talking about. So longer wavelength things are generally called as radio waves. You must have opened up some kind of FM radio station in the morning, or maybe some days AM amplitude modulation and frequency modulation, short waves, long waves, SW2, short waves, number 2, Colombo, Ceylon, and all. You must have heard. Maybe some of us know of our age, we used to listen a lot of music and all from Sri Lanka thing and all. Okay. Your All India radio programs also are there. You know the wavelength? The wavelength is going to be kilometers. If one crest is in the Ambedkar Open University, the next crest is going to be in Oilfield, where my residence is there. So it starts here and goes on, falling down of Durgancheru. Still it is above the null point, and somewhere near that building, maybe in a very Meridian Hotel, it must have come to null. And after AM Mall only, it will go to the trough. Again, it will going to raise up somewhere in front of. That much is going to the length of the wavelength. So wavelength will not be. Don't think that light wavelength means in angstroms and nanometers and all. Light wavelength can be in kilometers also. The radio waves are going to be meters and kilometers. Okay. Then microwaves, some things may be meters also. Meters to kilometers is called radio waves, and meter to micrometers means 10 to the power -6 of a meter. That zone, wavelength zone, is called as the microwaves, where most of our cell phones are operating. Our cell phones, if suppose Sarah tells me that radiation, whatever is sending to the tower, is in microwaves. The wavelength is going to be micron, 10 to the power -6 of a meter, 1000th of a millimeter. That range is microwaves. And infrared is going to be again 1000 times less than the wavelength of a micrometer. Then visible radiation, whatever we see with our naked eye, with the specs or without specs, that is actually the narrow band. It is in nanometers, 800 nanometers to something like 400 nanometers. So within a span of 400 nanometers, all of us are able to enjoy the whole movies and our visual perceptions, all these things. So 800 nanometers to 400 nanometers zone is called as wavelength zone, is called as a visible radiation. and below that also, maybe something below 300 nanometers or so 350 nanometers to something like 1 nanometer is called as ultraviolet light, and 1 nanometers to 10 to the power of minus 10 means angstrom is generally called as X-rays, and even below angstrom, maybe even 1,000th of an angstrom, which is the size of a nucleus, is called as gamma rays. And even below gamma rays also there is some kind of radiation called as the cosmic radiation, which is not going to be very important for us. So, my dear youngsters, you have to understand light is a big highway. Okay, starting from that to this. If you imagine the order of radiations in terms of wavelength and all, if you say that one is the lowest wavelength known to us, 1 unit, lowest wavelength that is representing light, or the messenger of the so-called representative light is one unit as the shortest wavelength. The longest wavelength is going to be 10 to the power of 40. That much range is there for light. So light is not a small thing, even though you see light here and all, but you have to appreciate light is not only the light, whatever you see, what you take a camera put and all. Light is very big drama, big chakra, big samaram. Okay? And nothing in the universe has got that kind of length. For example, human race. What is the shortest fellow available? Maybe newborn fellow, maybe 1 foot. Who is the tallest fellow in the world? Maybe 2 meters, maybe nobody has got 8 meters, like 8 feet, let us say. So 8 feet to 1 foot. So 1 to 8, only 1:8. 1:8 is the range of human race with respect to height. But what is the range of light? Shortest fellow to longest fellow. 1 and 10 to the power of 40. Means 1 and after 1 we put 40 zeros. That is going to be the extension or breadth of the power, and all of them are going to be one race. Like human race, they are going to be called as a electromagnetic race. That is how you have to appreciate. Now, with respect to consolidate or to recapitulate what are your learned so far. Longer wavelength means low frequency, low wave number, and also low energy. Medium wavelength means medium energy, medium frequency, and medium wave number. Short wavelength means higher energy, higher frequency, and higher wave number. That is how you have to keep in mind as a rule of thumb. Now, coming to the point. Interaction of radiation and matter. Sir, you told so far light is nothing but only oscillating electric field, oscillating magnetic field, and you told that they stay together like a coin with bomma bursu, with the head and the tail. That much of light, irrespective of the amount of frequency or amount of wavelength you are having. You told that the range of frequencies, range of wavelength is 1:10 to the power of 40 and all. Okay, let it be there. But light has got only simple behavior, simple phase, simple description, simple biodata. Okay, frequency, wavelength. That's the language. Wave amplitude. So 5 things you can say, 5 characters. BSc, MSc, SSc, PhD, MPhil, all these things are not there. And they was associate professor, dean, these are all are not there. Energy, amplitude, wave number, frequency, wavelength. That's all only. But with this simple thing, it is going to be interact with the matter. Matter means what? Elements themselves, known elements themselves are 92 different elements are there. Forget about their isotopes. 92 known things up to uranium, but trans-uranium elements are actually synthesized. But if you think in terms of isotopes also, maybe 1,000 different kinds of elements are there with us. Carbon itself, with a simple atomic number 6, is going to be existing in the 20 different isotopes. So-called presently graphene, graphite, fullerenes, boggu, coal, and diamond, and charcoal. Lot of things like that. Once you talk about this nanotubes and all, what nanotube? Nanotube, inside nanotube, coaxial nanotubes, one bottom, inside bottom, the bottom, chinna bottom. So all these are different materials, but all of them are having only carbon. but with different hybridization, sp2, sp3, etc. Okay, diamond sp3, there's a unique fellow, but all other things are going to be sp2. But within sp2, there's going to be curved, multi-gonal, polygonal, polyhedral. That way, in one carbon itself, if you are able to find out 20 different things with the same isotope, carbon 12, I'm talking about 6 protons and 6 neutrons. But there are other isotopes of 6. Carbon 14 is there, which is NMR active. Carbon 13 is there, which is also NMR active. Carbon 14 you also use for dating and all, not the type of dating what we are regularly famous with. Okay, time dating, not evening dating, girls and boys. Okay, so that way, all these things are called elements. Then what about compounds? With carbon hydrogen itself, we are having hydrocarbons. The number of hydrocarbons known are not less than 10,000 to 1 million, 1 lakh. And different compounds, hydrogen, carbon, and nitrogen. Hydrogen, carbon, oxygen, hydrogen, carbon, sulfur, hydrogen, carbon, and maybe some selenium, hydrogen, carbon, phosphorus, organoboron. And if you count within the organic chemistry, you are having millions and billions of compounds, but made up of within this known elements. So this 5 characteristic fellow, right, is going to be interacting with so many billions and billions of materials, both elemental as well as compounded, and it's going to tell us what material you are having with you. Is it carbon in a so and so manner? Is it oxygen in so and so manner? Is water in ice form or a liquid form or gaseous form? Or it is a sulfur in the yellow sulfur or a red sulfur, this and that. So this fellow is having lot of intimacy, lot of interaction or playing with the matter. And these are the various ways in which light can interact with the matter. Okay, reflection. In the morning, all of you are getting dressed, must have seen your face on the mirror, and you put lot of powder also. You might have combed. So all these things are reflection. You were some light. You can't use mirror in night, no. You can't use mirror in pitch dark room. You have to have some light. The light falls on your body, depending upon the type of contours, depending on the type of the dress up or outfit for having, or the body, different ways light is going to be reflected. On the teeth, nothing is there to observe, everything comes out. That's why it's like white. On the hair, after drying me, I have dried up, after drying, we are going to have nothing reflecting. So depending upon the reflectivity, you see your face, or I see you in front of me, you see me in front of you, because that's reflection property. And refraction. Refract is something where you get a light in one medium, and from one medium to other medium, that's called intermedial zone or interfacial boundary. But the interfacial boundary, the light does not go straight. Maybe in our high school days and all, we had that light travels in straight line. That is what you say, no? It is a subject to conditional statement. So if you go and ask a kid in the 8th class, 9th class and all, they will say, how does light travel? No, sir, light travels in straight line, they will say. But really, does light travel in straight line in a given medium? So, in a given medium, light may travel in straight line, provided the medium is homogeneous. The medium itself is mixed, light may zigzag, may go in the zigzag. So, what you have to understand is that refract means the bending of light line between media. Okay, then dispersion. Because of refraction, different wavelengths will be refracting in different ways, and that is going to be resulting in the dispersion that's creating light colors. So colors will come. And remember, all of us are able to see because of scattering mode. So after reflection, the light that's reflected on a mirror, no, is a flat one. So the incident angle is going to be same as the reflecting angle. That's okay. But in case you are having a rough surface or non-reflective smooth surface, then the incident radiation will not be having same kind of reflecting angle. Some depending upon the contour here, some may one portion of this. Suppose my 4 fingers of the light beam. One beam may be falling on a zone that is this way, so it will come towards me. and the other beam may go and fall on a surface which is in this manner. So it will fall there and it will go that way towards Kodesara. But the light is falling on a rough surface will be reflecting into different sides, different directions. That's called as scattering. Because of scattering only you are able to see the world. Don't think that reflection is the reason for seeing the world. It's mostly because of the scattering you are able to see us. I'm able to see the white chart here. I'm able to see the cartoon here. I'm able to see this and all. I'm also able to see everything here. I'm able to make a walk properly without getting hurt, without getting obstruction and all. Because of scattering of light only, not because of reflection. Scattering is one of the important things. Then the emission and the lights are emitting, the radiation coming from lamps or LED screen, you are able to see this particular screen. Light emitting diode, it is emitting radiation. And so that way, radiation has got some friendship with this light fellow. There is a LED component is there, some kind of semiconductors are there. So they are actually interacting with radiation to give emission. Emission one thing. Then the diffraction. Diffraction is the scattering of radiation on a sharp object, not on a plane position, on a sharp point. So on a sharp point, if you have monochromate radiation, it need not be polychromatic radiation like multiple wavelengths need not be there. Even a single light, single wavelength light is called monochromatic radiation. Even if you are having monochromatic radiation, with that monochromatic radiation, if you are having 4 beams, this is yellow line, this is also yellow, this is also yellow, this is also yellow. Like that is a beam of yellow light or beam of blue light falling on a sharp edge, and depending upon the way in which, depending upon the phase in which they are falling on this sharp edge, they may get different directions. And once they go to different directions, they may interfere. The crusts may join together, giving you bigger crust. The trough may be joining, giving you bigger trough, or the trough may be joining with crust, it may give you 0. This is called interference. So the diffraction pattern may also lead to interference. That's why the diffraction and interference are almost coexisting together. Then absorb, this is going to be the point where I am going to spend the remaining time. Okay. Then the transmission. Absorption and transmission are going to be corollaries. Means whatever, see, the materials know if they love that light, if they are interested in that light, there is some kind of quantum mechanical guidelines. Depending upon the quantum mechanical guidelines, if they are able to swallow the light, to a certain extent, the light is swallowed. The portion of light that has been swallowed, that has been grasped to do certain job inside, to perform certain quantum mechanical job inside, quantum mechanical task inside, okay, out of the radiation, whatever you are sending, that portion is called as absorbed light. And whatever portion that has not been used up, whatever has been that has not been consumed is coming out. That particular portion of light that has not been consumed is called as transmitted light. So transmission and absorption are like profited loss. Okay. Then polarization. Even if you are having a monochromatic radiation, the monochromatic radiation is oscillational. Suppose I am talking about only electrical field. Electrical field oscillation may be on a vertical plane, maybe on horizontal plane, maybe on an inclined plane or inclined plane like that. So multiple planes of oscillation may be there. So this is that way, this way or this way. So that is called as a non-plane polarized light, maybe monochromatic. So a non-plane polarized light, if you are sending through certain materials called polarizers, it may filter off the remaining things and oscillate only in one plane. That's called a plane polarized light. So polarization is one of the important attributes of light. So these are the, okay, what do you say, the 10 commandments or the 10 rupas or the shavakaras of light have to be understood. So whatever you talk about light, that has to be either one of them or multiple of them. So, for example, your rainbow visual perception is simultaneously due to reflection, the so-called total internal reflection, and also refraction, and also the so-called interference. Okay. Now, this is a reflection of radiation, and from wave theory, you may call this way, or from quantum mechanical theory, Einstein's quantum mechanical theory, light is made up of photons, right particle, which is a boson, and that boson comes out and falls over here and gets reflected. So reflection concept is understood in this manner from high school knowledge and all. Then how are we going to be benefited by reflection? Okay, interaction of radiation, origins of spectroscopy is the title. Okay, origins of spectroscopy, everything in that is spectroscopy, but something useful for a chemist, for the material diagnostics, for understanding what it is, how it is composed of, to understand that. Okay, reflection is actually available knowingly or unknowingly to some of us. Maybe I don't know whether you are already aware of that. There are a lot of spectroscopy techniques based on reflection. Okay, specular reflectance spectroscopy, then grazing angle reflectance spectroscopy. So in NIT Warangal, when I was dean, we have nearly purchased nearly about 2 crores or 2.5 crores worth of spectrophotometers, and we made it very mandatory to get this gadgets also, to these accessories also. For example, suppose some material is not soluble in any medium, then a solid component itself you can just measure for IR spectrum can be taken. Only thing is on a smooth surface you have to have the powder, and the IR radiation after Fourier transformation comes and touches this little compound and gets reflected. Okay, this is called specular reflection, specs, because specs means the particles. Okay, particle-laden material, depending upon the way each of this particle is composed of, the outgoing radiation will be carrying the address, carrying the image, carrying carrying knowledge of this material. Incident radiation is going like a jet, going like a boat, but in the boat, on the grain, the specs, after doing some kind of listening or hearing, some judgment will be done. With the judgment accomplished, with the judgment carried, the radiation comes out and you'll be detecting it by the detector. So, what is the kind of radiation characteristics this reflected radiation is giving with respect to incident radiation? By that, you'll be able to understand some nonsense about it, some knowledge about this material. That's called as the specular reflectors. Similarly, grazing angle. Grazing angle is what is meant by grazing. So the cattle and graze, what do you say, the green things, no? So grazing అంటే గడిజన లంచగొడ్లు గడిజన కాదు, మనకు పశువులు మేత మేయడం, దట్స్ కాల్డ్ grazing. So the radiation goes very, very closely to that, and it just goes like the cow grazes, like the buffalo grazes, no, it mingles with that material and comes out. So that way there are some techniques in spectroscopy using reflectance. Similarly, this is the meaning of grazing, that way radiation is good. Then refraction is what you come across. Suppose you put a pencil in a glass without water, it looks very straight, but if you put water, no, it looks as if broken. Because of that, it is because of this so-called apparent view and total view. So because of that, no, it also looks rising up. Suppose you put a coin on at the bottom of a glass and put water, the coin seems to be lifted up. That is the refraction. Okay. Then how is the refraction useful for chemist? Refraction is useful for chemist. Maybe in most of the degree college laboratories, Abbe refractometry very common. It's very simple. We also got something like 4 or 5 such instruments are there in NIT Warangal. In even in civil engineering department also we have got, in chemistry we have got, in chemical engineering we have got. So oils and all, they just measure the refractive index. Okay. So the refractometer is one of the instruments here. Abbe refractometer. The method is called refractometry, and the homologous series. For example, methanol is there, liquid. Ethanol is there with one CH2 group adding up. CH3OH, CH3CH2OH, CH3CH2CH2OH. Okay, propanol. CH3CH2CH2CH2OH, propanol. CH3CH2CH2CH2OH, propanol. And it may be branched also. Then all of them are liquids only, but the refractive index will be different. So homologous series CH3 CH2 n times OH, where n is ranging from 1 to 0 to any number, the refractive index is going to be a negative sum. Methanol's refractive index and ethanol refractive index, propanol refractive index, N-propanol again, N-propanol refractive index, and N-propanol refractive index are going to be having some kind of relationship, maybe multiple by 1, multiple by 0.5, multiple by 0.3, etc. So by looking at the refractive index, with respect to methanol, I will be able to tell even without going to NMR spectrum and all, I can say, my dear friend, it may be having hexanol with you. I think you have given me hexanol, I will say. Very broadly, it may not be hexanol, but with 80% conformity, I can tell it is hexanol. And this is one of the important things. And that particular property called the Frog R. So we will be measuring the Frog R also. And the radiation matter dispersion also is there. I told you dispersion is polychromatic radiation becoming multiple lights like that, and your rainbow is because of that. And then where do you come across the dispersion? The dispersion, okay, biology people will have to use this optical rotated dispersion. Without optical dispersion spectroscopy, there is nothing like biochemistry now. You are able to find out these primary, secondary, tertiary structures of enzymes, proteins, and all by the so-called optical rotated dispersion as ODO and polarimetry. The polarimetry is going to be the so-called angle of polarization, or angle of polarization. Okay, rho or theta you call it as. Sugar is you say that there's two rotatory. Fructose is levorotatory, you call. No, what will be that? A plane polar light upon incident, once it goes out, it's going to be making a counterclockwise plane. And in sucrose or glucose or the so-called sugar water wheel, it's going to be making toward the clockwise direction, called as a dextrorotation. So the levorrotation and dextrorotation is due to the polarization. Okay, now that polarization angle, the polarization extent of polarization angle is going to be related to wavelength. So wavelength related polarization is called as dispersion. That's why it's called as optical rotated dispersion. It comes to this is the optical rotation for this wavelength. This is optical rotation for this wavelength. This is the optical rotation. The optical rotation is the rotation, molar rotation is a function of wavelength. See wavelength. So that is called as dispersion. And there is one instrument also called as a CDOR, the spectrometer. And we have got such instrument in the NIT Warangal. Then scattering, I told you scattering is the reason why we are able to see materials, the white material, blood material, the red material. The fact that it is red and is not only because of absorption, but also because of scattering. See, for example, white is looking reddish now because the white light is falling over here. Except red light, other radiations are absorbed by the material here. Whatever paint is going over here, that paint actually allows all other colors in the white light except the red. It does not like red. And if it is actual reflection, light is falling over from here, it must have been seen only by me. It is not able to see. Because light is incident wavelength, incident angle, and reflection angle. Okay, maybe scattering characters. So I should only be able to see that. But you are also able to see that. Why? What does it mean? Scattered. Scattered so that he is seeing. And you are all seeing because satellites coming towards you, satellites coming towards them also, satellites coming towards me also. So radiation, even though they are falling only from, even other lights are off, only one light is there, the light comes and travels straight line over here because the uniform phase, uniform medium. So light is coming over here and it should reflect the same angle, but why it is reflecting, why it is not reflecting the same angle and is seen only by the fellow who is actually situated at the reflecting angle, but all of us are at different angles because of scattering one. So that way scattering also is one of the important things by way of which you are able to observe materials all around. But how it is going to be useful for a chemist? It is going to be useful for chemists because of various things. There is something called a Javalance diagram. The fate of radiation once it goes and falls on materials, it may undergo different consequences. The radiation may undergo different aftermath. The so-called incident is the starter. After incidenting, what will happen to the radiation? That particular story is non-chemical story is called as a Javalance diagram. So fluorescence, phosphorescence, all these things are actually that. And Raman spectroscopy, our proud son of India, who has got the only Nobel Prize for India so far, from 1930 is Raman spectroscopy. So Raman spectroscopy also is scattering technique. That way, scattering is a phenomenon which is actually resulting in different kinds of spectroscopy techniques, especially in Raman spectroscopy. Raman spectroscopy itself is multiple branch. SAS is there, okay, and laser Raman spectroscopy is there. Then emission, and I told you emission is nothing but radiation coming out from a source. Okay, this is called emission. And emission, how it is useful for a chemist. And there is one instrument called as IC2OS, inductively coupled plasma optical emission spectrophotometry, atomic emission or molecular emission. And fluorescence and phosphorus is also one kind of emissions only. We call them together. Fluorescence and phosphorescence together are called as luminescence. So luminescence spectrum is both the fluorescence spectrum as well as the phosphorescence spectrum, depending upon the timing. If the radiation is coming out from a material only when incident radiation is there, that's called as the fluorescence. Even if you are removing the incident radiation, but still the light is, if the material is looking shining, it is called as phosphorescence. So both are going to be possible. The fluorescence and phosphorescence both are possible only upon some radiation falling on that. Okay, so that is the light coming out of incident some radiation is emission only because the light is coming out from the material. But what kind of emission you are talking about? Delayed emission or instant emission, or maybe induced emission. So this is called as inductively coupled plasma optical emission spectroscopy, which is the best analytical tool available so far in the world. Okay, what is the lowest concentration a chemist can measure? Is called sensitivity or analytical sensitivity. The best analytical sensitivity available for a chemical human being or a chemist in the entire world is IC2OS. With that, we are able to measure a concentration as low as 10 to the power minus 12 of a molar. Okay, 10 to the power minus 12 moles per liter. Such a mild, faint solution concentration also will be able to measure. There is no other technique which is capable of measuring 10 to the power minus 80,000 molarity. Okay, maybe insects can measure. Insects, suppose in the entire Ambedkar Open University, we have a huge campus, maybe 100 kilometers maybe there, or maybe, sorry, 100, how many acres, sir?
84.
84 acres are there. But even in these 84 acres of land, in case we are having 10 molecules of some compounds, okay, and the insect can find it out. So it goes to the flower. Okay, pheromones, called pheromones. So that way, the emission also is useful for a chemist. Then we talk about diffraction. Diffraction is one wave becoming several waves. Okay, if you are having a CD and you see different colors on that, that's because of the diffraction only. Diffraction and interference, they go together. That's why I'm putting them together. And because of the diffraction only, we're able to see the molecules structure, the molecular structure. Single crystal X-ray diffractometry is one of the most important techniques by way of which you are able to see which atom is where, which atom is here, which atom is away. How the atoms are actually built together, how the atoms are actually situated together by a chemical bond to make the entire molecule. That is possible only with X-ray diffractometry. There are two kinds of X-ray diffraction techniques: powder XRD, powder X-ray diffractometer, and also single crystal X-ray diffractometer. With powder XRD, you will be able to find out the unit cell dimensions. But with single crystal X-ray diffractometry, you will be able to find out the entire molecular structure if the crystal is very clear. So this is a very well-known single crystal X-ray diffractometer, which is there in Central University, and which is also there. Powder X-ray diffractometer is there in Varangal. We are also planning to get one single crystal X-ray diffractometer. You know that a single crystal X-ray diffractometer costs not less than 5 crores. Okay? If you want to get a nice one. Then the interaction of radio polarization. I told you polarization is the radiation plane making only one planar oscillation. Okay. With this principle only, all our 3D pictures are there. When you go to a 3D movie, okay, I'm near the gate now, that particular fellow, but I've given you some specs, black looking specs now. But you know what they are? Maybe here in the goggles, whoever are using goggles, no. unless you are having a differential a site issue, both of them are going to be identical things. Okay, but in 3D movie, both the glass are not identical. In one glass, radiation that oscillating only in vertical plane will be propagating. Radiation that is oscillating in other planes will be cut off by this. And this particular right side eye glass is going to allow only radiation oscillating on a horizontal plane, but will cut off all other radiations oscillating on any plane other than horizontal. Only horizontal wave come over here to my eye. So right eye see only radiation from the screen. Suppose that is a 3D screen. Radiation coming from the screen in this manner will be going through this, and my right eye will see that. And the left eye sees only radiation from the screen radiating or oscillating only vertical plane will pass through this, that will be perceived by me. Now, when I'm seeing them, so there is one fellow far away from me, one fellow closer to me, one fellow right side, one fellow left side. So 3D means what? Not only the plane X, Y, but the Z also. So 3D, the depth also. We will not be able to see depth here. There is no, you will not be able to see that person who is actually away from him is also available on the screen only. He is also seeing on the screen only. So you are not seeing depth. So in 3D movie, you see the depth. Why? Because the fellow who is farther will be, that fellow's radiation will be coming in a horizontal manner. So my right eye sees him and left eye sees only the front fellow. Front fellow is seen by left eye, part of fellow is seen by right eye. My brain actually composes. Okay, then I will see that I think his deeper is the front. So the 3D picture image you are able to perceive only because of the concept of polarization. So that's why I will just give you some kind of simple toy sort of experiment. When you go next time for a 3D movie with friends and all, because you cannot hold this because the fellow will curse you. You take your friend's goggle and put the right goggle on the left one. Vertically, you see black. So far they look transparent. But once you put the right glass on the left or left glass on that in this manner, they look black. Why? Because they are cancelling off each other. That way, polarization is one of the important attributes used of. Now, how it is useful in for chemistry? So, polarimetry, optical rotate dispersion, what I call circular dichroism, and polarimetry, sugar, how much dextro rotation it is at 25 degrees. So, that way, the polarization also is part and parcel of our life. Lastly, 10 minutes. Okay. So, lastly, we are going to talk about the absorption spectroscopy, which is actually the importance of all other kinds of spectroscopy things. Okay. Because the story is simple. Even though absorption and transmission are going to be the cornerstones or maybe the cardinal for hundreds of scopy techniques, the simple thing is this. The simple thing is that you are going to, the colors are because of that only. Absorption and transmission is responsible for colors, various colors, whatever you see. Okay. Suppose I am sending some radiation with a big amplitude called as I0. Incident radiation is intensity. Incident radiation intensity is very big. But suppose somehow this light has been useful for this particular material. So to that extent, it's traveled off, giving you leftover light. The leftover light is called as the transmitted light intensity. So transmitted intensity, incident intensity, they are having some kind of relationship. And percent transmittance is called as how much transmitted with respect to the incident radiation in terms of 100%. So IT by I0 into 100 is called as percent transmitted. Okay. That is how much is left over. But in terms of how much has been swallowed, you got another parameter called absorbance. The absorbance actually has been defined as the I0 incident radiation over transmitted radiation or log of that. Okay, that's called absorbance. Okay, this absorbance is related to concentration by B-Lambert's equation. All these things are known to you. That is a different matter. I am talking about only how the radiator is able to make some kind of interaction, make some kind of handshake with the material. So the handshake is this. The higher intensity, broad means not band and all, it's only intensity we are talking about. Intensity is very higher, intensity is very low here. So then because transmittance and absorbance or actually IT and I naught are there. So A is also called as a D 2 minus the log percentage transmitter. This is how the absorbance and transmission are the interrelated. So again, why do you get excitation? Why do you get absorption? Absorption is possible because in material there are quantum mechanical states, energy wise. Quantum mechanical state means energy wise. So energy in the materials actually is quantized, we say. Low energy, in-between energy, in-between energy. The energy is not continuous, not like a ramp, not like a wall. It is either this energy, or this much amount of energy, or this much amount of energy, like a ladder, like a staircase. So in case there are some rules also called as selection rules, depending upon the type of material we're talking about, what light will be taken up, how many steps simultaneously it can jump. All these things are there. So the so-called selection rules, delta J is put plus or minus 1, delta V is put plus or minus 1, delta Q is a delta plus or minus 1. Like that, some rules are there. Whatever it may be, one state to other state, light is actually useful, light is actually for the purpose of the system going from ground state to exist. So that is possible. So because you don't know what light it allows, so you send the pulse radiation without any knowledge, very innocently, it will select a particular light. Suppose I'm talking about permanent solution. Permanent actually allows only green light. So green light will be the previous one. Green light alone will be swallowed. Green light alone will be decimated. Green light alone will be falling down. Yellow will be remaining as yellow. Red will be remaining as red. The same intensity, but the green will be falling down. Whatever, whosoever actually absorbs green light will be looking in the pink manner. Whosoever actually absorbs red more will be looking in green. The leaves, the plant leaves, whatever you are seeing as green, they love red light. They like red. Since they are stallion mostly red and orange, the other light, mostly the blue, green, yellow, other violet color. So violet is very faint, will not be more dominant. So green is going to be more dominant. That's why they look green. That way, out of this colors, whatever color is actually loud, that radiation is actually matching this gap. That delta means energy gap between the excited quantum mechanical state to ground state quantum mechanical state. That delta E is going to be built. That's going to be balanced by certain frequency, certain wavelength, certain wave number. Other wavelengths will be sent out, transmitted. Other radiation will be transmitted. One radiation will be less transmitted. So this is the way in which you have to understand the concept of absorption. And absorption is given by that. So for example, if I am sending a radiation one after the other, slowly, and let us say this is the cuvette where my solution is there. Now red light is going, yellow light is going, green is going. Out of, so every radiation has been exposed to this. So it's like a buffet. So you are giving a lot of dishes there. There may be vada, there may be idli, there may be brinjal curry, there may be fish curry, there may be chicken curry, there may be pappu. All these things are depending on my choice, depending on my culinary habit. I will choose some. I will left out other things. Somebody else may choose this. Somebody else may choose this. But nobody will be taking away everything. So there will be some 64 dishes coming in some multi functions and all. Okay. So whatever is tasteful to you, whatever is palatable to you, whatever is delicious to you, that only you take. Other things you just discard. Same way, depending upon the nature of materials, out of all these colors, one will be taken up, others are one or many, depending upon the number of quantum mechanical guidelines. For example, in the infrared spectroscopy or so-called luminous spectroscopy, there may be several kinds of operations possible. A bigger gap oscillation, or smaller gap oscillation, and medium gap oscillation. So if all the three gaps are compatible to light, so those three gaps are going to be built by three different kinds of frequencies. Only those frequencies will be traveled, other frequencies will be sent out. That way, the IR spectrum is going to be, I mean, get a dip here, that means that the light has been swallowed. There's no gap here, there's gap here. This light has been absorbed. This gap here. So these are called as the transmission spectrum. This is called absorption spectrum. Absorption spectrum and transmission spectrum are going to be upside down. If transmission spectrum, wherever absorption is there, the peak will be falling down. So low transmission means nothing is coming out, or nothing less is coming out. So in absorption, more is absorbed, less is absorbed, more is absorbed. So that way, low means no absorption, up means more absorption in the absorption concept. In transmission concept, this way. So that way, I am sending multiple colors depending upon this taste and the compatibility, quantum compatibility, the radiation is going to absorb, and something is going to be transmitted out. So now there are two different kinds of absorptions. One is atomic absorption. The other is molecular absorption. Atomic absorptions are very simple because I told you one thing before I leave in the next 5 minutes. Let me tell you one thing. Lastly, unless light, I told you what is the behavior of light. The nature of light is what? It is electromagnetic field, simultaneously, sinusoidally oscillating electrical field and magnetic field that is called as light with different wavelengths, with different frequencies, with different wave numbers, different energies. Okay. That radiation, which is electrical field and magnetic field, simultaneously must have to have its own common gene inside the matter. Particular common gene, there should be inside this material. Suppose I am light. If I want to make some kind of interaction with this fellow, I am simultaneously oscillating electrical field. I am simultaneously oscillating magnetic field. I see this. In this material also, whether it is atom or molecule, whatever it may be, I should be able to see some oscillating electric field or oscillating magnetic field inside. Then how do you get oscillating electric field, oscillating magnetic field inside this? It is not all in motion. So we have to talk about motions also, not the type of motions we go in the bathrooms and all. So molecular motions or atomic motion. Okay. Then depending upon that only, molecular spectroscopy is going to be realized. Atomic spectroscopy is going to be realized. And there are two kinds of motions. One is outside the material, means material as a whole is moving in the outside space. See, this is called as translational motion, like a pendulum, or maybe like a rail, like a bus, like a train, like a rocket, or like a molecule in the air. So we're able to see a lot of oxygen and nitrogen, or maybe some extent of carbon dioxide here. They're all making kinetic motions. They heat and go away. It's the so-called kinetic theory of gas, and all you must have understood. So they are called translational motions. The translational motions will not be giving you any sinusoidally varying electrical field or magnetic field for this material. So what kind of motions for this material can provide you oscillating electrical field and oscillating magnetic field inside, so that it can be having a dialogue with the light? They are possible only by rotational motions in the molecules, vibrational motions in the molecules, or electronic motions in the molecules or atoms, or nuclear motions in the molecules. So now I am going to spend 1 minute on each of them. Okay. So, okay, this is what maybe in absorption spectroscopy, depending upon the type of zone you are having, different absorption spectroscopies are possible. Radio waves are going to be useful for NMR spectroscopy, nuclear particle resonance spectroscopy, radiation spectroscopy, etc., Hector, Edgar, all these things are there. Then microwaves are going to be useful for rotational spectroscopy, rotational pure Raman spectroscopy. Then the ESR, electron resonance spectroscopy, is also called as the EPR, electron paramagnetic resonance spectroscopy. Then NR, electron nuclear double resonance spectroscopy. All these things are possible when you are using microwave radiation or the electromagnetic radiation. So using electromagnetic radiations of this zone are going to be microwave zone, are going to be giving you this kinds of spectroscopies. Similarly, infrared spectroscopy are going to be useful for realizing Fourier transform infrared spectroscopy, rotational Raman spectroscopy, attenuated transmission spectroscopy, then total reflectance spectroscopy, etc. are possible with infrared radiation. Then visible light, UV visible spectroscopy, photoluminescence spectroscopy, Raman spectroscopy. Okay. Then laser induced breakaway spectroscopy, then circular diaphragm spectroscopy. All these are possible with visible light. When you're using visible light zone. Similarly, ultraviolet zone, when you're using again UV visible spectroscopy, fluorescence spectroscopy, circular diaphragm, photoelectron spectroscopy, etc. are going to be possible using ultraviolet light. X-rays, okay, X-ray fluorescence, X-ray absorption fine structure, then X-ray absorption, nuclear emission spectroscopy, not nuclear, James, okay, nuclear absorption, non-emittive spectroscopy, X-ray absorption spectroscopy, X-ray photo spectroscopy or photo emission spectroscopy. Okay, then this energy dispersion spectroscopy, energy dispersion, X-ray diffraction spectroscopy, XRD, X-ray diffraction spectroscopy, etc. Then gamma rays, mass bar spectroscopy, then prompt gamma ray, neutron absorption analysis, neutron activation analysis, then delayed gamma ray, neutron activation analysis, etc. are there. So, depending upon the kind of zone you are having, every part of the light is having some kind of friendship with matter. Depending upon what kind of interest you are having with matter, depending upon what kind of information you are seeking from the matter, you can use different zones of this radiation and get benefited by that. Okay, as I told you in the beginning, previously that unless matter also has got something common with the light, but something common, oscillating electric field, oscillating magnetic field, it will not be carried out. So in classical theory, a continuous energy may be there like that, but in quantum mechanics, the energy is restricted, maybe either this energy or this energy or this energy. That is the thing. Similarly, rotational spectroscopy, the Rangu Ratnam, or maybe go around and up, but I will know the energy is going to be continuous like this. But in quantum mechanics, no, the molecule when it's rotating, so the energy is going to be quantum, this energy or this energy or this energy, this energy. They're all going to be different by quantum number, the rotational quantum number, for the rotating molecule. Okay, if the rotating molecule has a dipole moment, let us say this blue one is positive charge and this gray one is negative charge, and blue is coming this way, so it will provide a greater positive field here and a greater negative field here. When this comes this side and this goes that side, the positive field is becoming negative field is becoming positive field. So at this particular point, away from me, if there is a rotating molecule like that, let us say this positive, let us say this is a positive, this negative. So me, I am going to feel more positive field here, and no, because in lambda means vertical, means cos theta is cos 90 is 0 for me, nothing will come out, but it is not negative now. So previously I was feeling my energy was very high because field is this way, and no problem. Again this way. So I am now making a movement depending upon its motion. So there is a oscillating electric field by virtue of rotating dipole. The rotating dipole is creating beside it, in the vicinity of it, an oscillating electric field. So an oscillating electric field means what? Light also. So light loves that. So that's why the molecule with dipole moment only will be able to absorb microradiation to make a spectrum. Molecule like nitrogen, oxygen, carbon dioxide will not give you any rotation spectroscopy, because even though they are rotating, because like this, no, even though they are rotating, there is zero dipole moment. Whether I am rotating this way, I am having same kind of zero only. That's why rotating spectrum will not come for molecules which are rotating without any dipole moment. That's how you have to understand. So unless the materials have got something common with light, the light will not be able to get absorbed. Same with vibration. Normal vibration like spring and all may have a continuous energy upon the amplitude square. Whereas for quantum mechanical vibrator like carbon dioxide, maybe water molecule and all, the energy is going to be quantized as V is equal to 0, V is equal to 1, V is equal to 2, etc. Given by V is equal to V plus 1 of H nu, the quantum mechanical thing. So that way a molecule, maybe carbon monoxide or HCl, maybe oscillating like that. So naturally, suppose I am having this kind of molecule, what will happen? Suppose I am the unit point here. When the chloride is, or maybe oxide with negative charge, with delta minus, carbon is delta plus. Delta minus coming towards me, I will feel down. When going away, I will feel up. When again is going away by constriction, If oxygen is going away from me, I will be rising up. So the carbon monoxide's oscillation also is making me go up and down. So there's a point here, there's a charge point here, or maybe some kind of section point is there, which is oscillating depending upon the vibrational mood, vibrational phase of this molecule. So all those molecules, by way of which during vibration, if they are creating electrical field oscillation beside, then that radiation will be lowered by that. So that only in a mode of vibration, where there is a change of electrical equipment or electrical field, such mode of vibration only will be absorbed, but not others. Okay. For example, I will give you some last one. Okay, for example, water molecule is there. Water molecule actually has got three kinds of vibrations. The so-called symmetric vibration, asymmetric vibration, bending mode vibration. In all these things, for example, let's say dipole. Dipole is actually increasing, decreasing, increasing, decreasing. So then naturally, it is creating an oscillating electrical field. So radiation will be absorbed by that. What about this one? Previously, when the molecule is symmetrical, the dipole movement this way, it will go this way, go this way. So since dipole movement is a vector, even if quantity is not changing, the direction is changing, then also it means that the dipole moment is changing. So naturally, there is a dipole moment variation, electric field variation, that also will be absorbed. Let's see a bending mode. So up and down, the dipole is changing. This also will be absorbed. So light is going to be swallowed by this mode, light is going to be swallowed by this mode, light is also going to be swallowed by this mode. Okay, that way, these three modes are going to be swallowing such a kind of radiation where their frequency of oscillation is same as the frequency of light. The frequency of light that they allow, asymmetric mode, is 3756 cm light is going to be swallowed because they are also oscillating so many times per second. See, 11, 25, 96 into 10 to the power 9, that many times in 1 second, they are doing this. So that way, this is the mode of vibration, which is actually picking up a radiation whose frequency, whose wave number is 3652 nanometer, and the number of frequencies 10, 95, 75 into 10 to the power 9, that many times per second. So this is the bending mode, 1595 nanometer will be absorbed, and 47817 into 10 to the power 9 times per second they are happening. So this kind of resonance, the commonality between the motion of the material inside the story and the light is called as resonance. That resonance is going to be possible only when there is a changing electrical field or changing magnetic field inside the molecule. So lastly, okay. So carbon dioxide, for example, the carbon dioxide, so there is a number of movements are this way only, Raman spectroscopy only can find it out, but infrared spectroscopy cannot find it out. That's the matter. So this is going to be IR active. This is going to also IR active. This is also going to be IR active, vertical plane and horizontal plane bending. But symmetric stage is going to be IR inactive because there is no change in dipole moment. Whatever extent this goes, to that extent this goes, it cancels out. Whatever extent it comes out, comes closer to the central carbon. This also comes closer to the same extent to the central carbon. So the dipoles are cancelling off. So there is the net dipole moment variation is 0. That's why this is not going to be, the symmetric stage is not going to be IR active. Means infrared spectrum will not be coming out further. Raman spectrum only comes out further. So that's why you are able to see this type of frequency. Even though this wave number also is going through the water, that is not absorbed because there is no compatible concurrent oscillation that is able to take up this wave number. But this is going to be swallowed because this wave number is same as the wave number of this. This is going to be swallowed because this wave number and this wave number is same. So this light is absorbed. This light is also absorbed because this light through this wave number, there is no motion in the water. That way, the number of the oscillations, whichever are matching to the oscillations of light, only those light portions will be absorbed, other portions will be spit out. They will be sent out, transmitted out. That's why you are able to get some peaks, not all peaks. If all peaks are there, spectroscopy wouldn't have been realized. For example, carbon dioxide, I told you. Carbon dioxide asymmetric stage is happening this many times, that's why peak is there. And the symmetric stage is also there with Raman spectroscopy, but there is no peak here because light does not see that. Light is blind to that. So carbon dioxide cries, hey, I'm oscillating here, we are not coming to me, we are not going to me so that I can absorb you. No, light says that I cannot see you. Where are you? Where are you? It will say. Because there is no changing electrical field or changing magnetic field inside the carbon dioxide molecule by virtue of this particular symmetric oscillation. That's why light is going to blind to that. Whereas asymmetric variation, the bending, horizontal bending, vertical bending are going to be same frequency. That's why again peak is going to come. So carbon dioxide, even though it has got 4 degrees of it is picking up only 2 peaks, whereas water molecule is giving you 3 peaks. So that way, the molecular structure is also deciding what kind of lines are going to be picked up, what kind of lines are not going to be picked up. Lastly, this is the last slide. Similarly, molecules are also having not only rotation, not only vibration, but also electrons inside. The electrons are not static, they are clouds. They are available in different orbitals. Okay, bonding orbitals, anti-bonding orbital, non-bonding orbital, bonding ground state orbital, bonding excited state orbital, the sigma star, then pi bonding orbital, pi star, anti-bonding orbital, non-bonding orbitals, etc. So there are some selection rules also. The selection rules say that okay, since electrons are always in motion, there is always changing electrical field. That's why all electronic transitions are possible, depending upon the quantum mechanical gap. So that radiation delta E, whichever is matching as H nu, that H nu only will be picked up for L star transition. But as is a pi bond naturally will be having bonding pi orbital and anti-bonding pi star orbital. Only that radiation delta E, which is matching to that frequency nu, that one will be absorbed. So one peak will be there, another peak will be there, another peak will be there, and then sigma star also possible, another peak will be there, and then pi sigma star is there. Not like that. And the peaks are going to have different heights depending upon the so-called quantum mechanical possibility. That's called as a quantum mechanical transition moment integral. What is symmetry-wise permitted? What is not permitted? Forbidden? To what extent they are forbidden? To what extent they are allowed? That will decide the extent of peak height. So all these things are the knowledge of quantum mechanics, or the so-called simple symmetry and spectroscopy subject. I'm not here to talk about that. You call me again at a later stage to talk about only electron spectroscopy, to talk about only the Cartan method, to talk about only the infrared spectroscopy, NMR spectroscopy, etc. That's a different matter. In NMR spectroscopy, the nucleus spin is going to be, because nucleus has got charge, no, and spinning, it is going to create a changing magnetic field inside. So the changing magnetic field inside is going to be happening at the radio frequency zone. That's why radio frequency zone is going to absorb in NMR. And the microwave frequency is going to be absorbed by spinning electron. Because spinning electron is rotating in a inclined manner, in this manner. So there is going to be some kind of projection on the horizontal plane, maybe horizontal plane. The rotating magnetic field is there. So since light is also oscillating magnetic field, it also allows that. So magnetic field based absorption, electrical field based absorption, both are possible in molecular spectroscopy. That is what I want to tell you. So the molecular spectroscopy, atomic spectroscopy, all these things are possible because light is able to make some kind of dialogue, some kind of friendship, and some kind of handshaking with the constituents of matter, and because that only spectroscopy is related. That's why the title has been defined as the interaction of radiation with matter and origins of spectroscopy. Without light loving the matter, the spectroscopy techniques, hundreds of spectroscopy techniques would have been possible without that. So thank you very much for your question.
Thank you. Actually, this concept, only the fundamentals of radiation, but when we are coming to end of the session, it reaches to peak level. I hope first 10 minutes, 15 minutes you can observe easily, but the latter enter lecture, it is very difficult to observe you because it is most higher than after degree you are encountered these topics in MSc level, MSc chemistry, MSc physics, MSc zoology, botany. But it is very much helpful to you for your future studies also. I thank you very much, sir. Now I request Praveen to propose vote of thanks.
It took nearly 90 minutes. Can you questions are there at least some 5 minutes? So you are.
Is there any questions, please?
For 5 minutes, okay. Yeah.
So you said on the wavelength slide, there is a craft and the draft. Can we call it as the antinodes and the nodes?
Antidote, yeah, of course, in inside they will know the point where zero amplitude is called as a node. But similarly, in interference also, suppose a crest is matching with the trough, then also the balancing zero will be there. That's also called a node. Okay, the nodes are the non-oscillating point in space and time. And antinode is a trough and crest. These things are called as antinodes because there is a finite amount of displacement of the unit charge or unit pole. So wherever intensity is a non-zero, it as a non-node or antinode. Wherever there is a zero sinusoidal wave intensity, that is called as node.
So the length of the nodes will be lambda and the length of the antinodes will be lambda by 2. Right?
Antinodes, see.
Where is it?
There.
What is that? Please asking.
Yeah, antinode for antinode, the length is lambda by 2. In between the two nodes, it will be lambda. She's asking.
In between, see, node. See, I told you node is 0 and 0 only. Amplitude twice. See, consecutive nodes is going to be half lambda, but that cannot be called as lambda because at one node, the next moment the wave may be coming up, making positive slope actually, called as a tending to become higher than 0. Okay. Whereas next node, immediately after that, it is tending to go to negative side. Okay. So that is also node, but that consecutive nodes difference is called as lambda by 2. But what is lambda? Lambda means two identical phases. For example, if you select a negative node, let us say, immediately after the node, it is projected towards down. When is the next point in the position or next node, where again the wave is falling down? That is again the wavelength. Node to node is half wavelength. Node to identical node is called a wavelength.
Thank you.
Anything else? One more question if you want. Okay, I think